have taken the example on PPT. It is not there right now, but example was that what should be the length of the packet? What should be the length of the packet such that when you're using in a CSMA CD network? Okay, so if you remember, you can watch the previous lecture. I've taken an example where TP was 1 millisecond and bandwidth was 1 Mbps, and I have asked that what will be the minimum amount of data packet size when you are transmitting in CSMACD. Okay, so the example that is from this particular formula you can easily able to find it out, because TT is greater than or equal to 2 into TP. So actually, you know what the TP here is. So TP is length over length of the packet over bandwidth. So it can be taken like this: length into 2 into TP into bandwidth. Okay. So this is the formula if you want to find out the length of the packet in CSMACD. So now we are, I think, at the efficiency. What is the efficiency of CSMACD? Because I'll take another. So I'll go to another lecture. Okay, so now what will be the efficiency of CSMA CD, or it is most probably referred to as Ethernet also. Okay, so sometimes it is referred to as efficiency of Ethernet, but keep in mind Ethernet and CSMA CD is one and the same thing, because it is most popularly used in the Ethernet. That is why it is referred to as efficiency of Ethernet also. Okay, so if they ask you efficiency of Ethernet, it means they are asking you efficiency of CSMA CD. Okay, so now I am only talking about the worst case. If you remember the worst case, in that worst case, if this was the example there, that there is a, there is a B, I've taken the example. Okay, so in this worst case, A will know that the collision occurs at 2 into TP time. Okay, so in the worst case, the A came to know about what time the collision will occur. Okay, so you can say that 2 into TP time is actually wasted for every collision. So you can say that. So to detect the collision, I am wasting 2 into TP time for every time a collision occur. Okay. So now what happens if I'm able to find out the efficiency of CSMACD? So suppose now you cannot say that every time your transmission will be successful. Okay, so for a successful transmission there will be many unsuccessful ones. Okay, so suppose in the time slot uh, when this A is sending the packet to B, so it will absolutely require at least or equal to 2 into TP time. So you this already know. Okay, so it is saying that for this amount of time you are doing nothing, you are sitting idle there. So this much amount of time will absolutely be wasted if your communication is successful, or if your communication is unsuccessful. Suppose this is your unsuccessful communication, so there is a collision. Now after some time you will again try to transmit the data. Suppose again you try to transmit the data after some time, again this particular attempt is unsuccessful. Again you try to send the data, and again your attempt is unsuccessful. Okay, so there will be many unsuccessful transmission after you successfully transmit the data. Suppose this is your unsuccessful attempts. Now after some time you will be able to successfully transfer the data. Now suppose if this is your successful transmission, the successful transmission only require the transmission time and your propagation time. Okay, so because there is no collision there, so if it is successful, this much amount of time is required for a successful transmission. Okay, so again if there is another unsuccessful one, you again have to wait for 2 into TP, 2 into TP, 2 into TP. So this particular thing will go on further like this. Okay, so again if there is a success, then the time for successful communication, the time will be the time taken to put the packet onto the link, and whatever is the propagation delay. Okay, so you already know that. Okay, So now if I want to find out the efficiency for CSMA CD, you already know the formula for this one. Is it, the formula for this one is your useful time over your cycle time of or total time. Okay, so useful time or cycle time or the total time. Okay, so now what is the useful time here? So I'll say my useful time always will be my TT. Okay. So for TT amount of time, I am doing, the station is doing some work. So propagation, when the packet is propagated, I cannot call this useful time, because propagation delay does not depend on anything. It is just that packet is going. So that station is not doing anything. So when the packet is going, the station is doing the station is transmitting the packet. Okay, so that is why the useful time in this case will be your TT. And now what will be the total time or the cycle time here will be, so the total time here for count the successful and unsuccessful one also. Okay, so if I am successful, suppose I am successful till here. Okay, so if I'm considering this as one cycle. Okay, so I got many unsuccessful attempts, and after some unsuccessful attempts, there is a success in the transmission. Okay, so what will be the total time? So successful one, the total time will be TT plus TP. So this is my success. When my transmission is successful, there is no collision. But when there is a collision, now how many times here the collision is occurring? Here the collision is occurring three times. Okay, three times. And how many time is wasted here? 2 into TP. Okay, so I'm taking only this case. So for a successful communication, so this is the total time for a successful communication. Okay, so now in that the useful time is the transmission time, and the cycle time or the total time is unsuccessful plus successful. Okay, so the successful time, in order for the packet to reach to the other end without any collision, the time taken for this is TT plus TP. And for unsuccessful one, the time is also should be counted, because I am counting the total time here. So unsuccessful, I have faced three collisions, and for that the amount of time will be 2 into TP. So we already know this. Okay, so if I generalize this formula, it will be TT over C into 2 into TP plus whatever is TT plus TP. Okay, so now this particular thing is for unsuccessful one, and this particular thing is for successful attempt. Okay, so how many collision it will the C donates the number of collisions. Okay, so it can be the number of collision can be zero also. So it is possible that in the first go there is no collision, you are able to easily transmit the packet. So this particular term will become zero, and the efficiency will definitely increase. Okay, so if you are able to transfer the packet in the first go without any collision, so the collision C will be zero. So this unsuccessful term will become zero, and your efficiency will definitely increase. Okay, but if there is a collision, it can be one collision, two collision, three collision, or it can be 100 collision also. So in that terms, your efficiency will, if there is some collision, the efficiency will definitely goes down. Okay, so now the term lies here. What exactly is the what exactly is the number of collisions here? Okay, so number of collisions. So how can you calculate it? Okay, so there are many ways you can calculate it, but in the end I am just telling you that the efficiency formula for CSMA CD is given as, if I solve the number of collision term, what exactly is the number of collision term here, then the efficiency formula of CSMA CD is given as 1 over 1 plus 6.448. Okay, so this is your main formula for CSMSUD. Okay, so I'll tell you some, because this in this particular the calculation of C, there are some underlying concept that will be used here. So the first underlying concept that you have already studied, it is probability. Okay, so I'll show you a little bit how can you calculate the C, but actually you have to have a definite knowledge for binomial distribution and Poisson distribution. Okay, so both of these distributions are used in the calculation of number of C's. Okay, so I'll show you, but do not definitely go absolutely into that, I'll show you that. Actually, I'll show you a little bit of this. How can you calculate this? Okay, so again, suppose there are stations, that there are many stations there, and every station has P. Okay, every station has P probability. I'll tell you what exactly is P. Okay, so now for successful transmission, so a successful transmission is when one station is able to transmit the data and others are refraining. Okay, so what is a successful transmission here? When one station transmit and others will refrain. Okay, so others will refrain. Okay, so it means that others will refrain from sending the data when one station is sending the data. In that scenario, my transmission is successful. Okay, so I have to find out what is the probability of success when only one transmit. Probability of success. Now again, this is simple probability formula here. Probability of success when only one station transmit the data. Okay, so so again, the P of success, I'm denoting this as P of success. Okay, so it will be because there are P stations here, so there are total so there are total n stations here. So, okay, so there are total n stations here. So what is the probability that one station is successfully transmitting the data? Okay, so there are n stations from NC1. So it is saying that from all the n stations, one station is able to transmit with a probability. This P denotes a success. Okay, so P is the probability that a particular station is transmitting the data, and others will refrain it from the remaining stations are refraining it. N minus 1 stations are refraining to send the to sorry, I'll show you. I'll just use a simple term. So out of n stations, one station will send the data, will propagate or send the data with P probability, and others will refrain with this probability. Okay, so if this particular scenario happens, then my probability, then I'll say that it is a successful transmission. Okay, so now this again, it is the simple. If you say that if you have studied probability, it is just when you are tossing a coin, provided that every coin at one time you will get a head that you want, and other times that you will get something different, something like that. Okay, so in order to maximize this value, I want to maximize the value or maximum value of success here. Okay, so if you want to maximize the value of success probability, you have to differentiate the terms you have to differentiate this P success equal to, differentiate it and equal to 0. Okay, so you can say D P success over dp should be equal to 0. Okay, so now you will have to differentiate it two times. You will see that the value is less than it will be less than 0. Okay, so now I'll again, I'm directly calculating it, that your p, when your p is 1 by n, your p of success is maximum. Okay, so your p of success is maximum. Now you can find what exactly you put the value of p here. Now what is the p value here in this particular term, that is success here? So it will become maximum success. Now when you will get maximum success, it will be nc1, and then it will be 1 into 1 by n, and it will be into 1 over 1 minus n. It is n minus 1. Okay, so if you calculate it, you will find that actually it is 1 over 1 minus n over n minus 1. Okay, so now again, this everything that I am doing here is to reach to this particular formula. Okay, so to find the number of collision, you have to know about the probability binomial distribution and Poisson distribution. Okay, so now after that you can the p, again I have to use some derivation and limit and derivation here. So p success Now it depends upon the number of stations. Okay, so it depends upon the number of stations, that is your n. Okay, so if your number of stations are very if your number of stations are very large, I say it will approach to infinity. In that you can do it a limit here, and tends to infinity for p success, max success, and for that you will be able to find that your actual answer is 1 over e here. Okay, so now this will be your probability of success, that is 1 by e. Okay, so I know that this is going very mathematics, so don't worry about it, though you don't have to do anything. So you just have to remember this particular formula, that is n CSMA CD is 1 over 6.44a after solving it for c. Okay, so again then uh, then now when you got 1 by e, if you're saying that 1 by e is the probability of success, so I'll say it b is the probability of success, then I have to ask, then how many times should I try before I get the first success? Okay, so then again this question is asked in Poisson distribution form. How many times should I try, should I try uh, before I get my first success? Okay, so this particular question is answered by Poisson distribution. So again, I'm not going what exactly is Poisson distribution. I'm just saying that after you solve it, it will be 1 over P max success. Okay, if you solve it, it will be 1 over E, and you will get a E here. Okay, so now E here is the number of collisions. Now E here is the number of collisions that we are finding out. Okay, so the number of collision before the successful transmission. Okay, so before the successful transmission. Okay, so now if you put the value of this particular number of collision in the efficiency term, the efficiency was c into 2 into tp plus tt plus tp, and it will be put the value of c here, c is e into 2 into tp plus tt plus tp. Okay, so after you solve it again, there are, if you have to well see the value of this one e, and if you put it, you will get actually your value, you will get the answer as 1 over 1 plus 6.44a. Okay, so that is how your efficiency value by the calculation of c. Okay, so by the calculation of c, your c here is now e. By the calculation of c, you are getting at this particular point. Okay, so again, you do not have to do these many calculations here. You can only see that the c is equal to e, that is already equated out. Okay, so that is already equated out. I'm just showing you a little glimpse of the calculations. Okay, so if you want to go into deep, you can refer to these calculations in your book. They are given there. You can directly go into deep, but I don't think that this is much of a use. Okay, so you can directly see that the number of collision is calculated as e, and by solving this particular equation you got the efficiency for CSMACD. Okay, so you only have to remember, so I'm only telling you the first time I'm telling you to remember this formula. Okay, so because if in your exam you try to drive it out, it will take a lot of time for this particular thing. So that is why I'm saying that for this particular purpose you just remember the formula here. Okay, so the efficiency formula for CSMACD is given by 1 over 1 plus 6.44 a. Now here a, you already know a is your TP by TT here. Okay, so now if you analyze it, it will be efficiency over 1 over 1 plus 6.44 a. Now here a is TP over TT. Now if I just extract out or put the value of TP and TT here, so what is TT or what is TP? So TP is your distance over velocity, and TT is your length of the packet over bandwidth. Okay, so now if you take a look at it, you will see that that your efficiency is inversely proportional to your distance, yeah, it means that if your distance is higher, if the distance is higher, your efficiency will be lower. Okay, so it means that it is preferred in LAN. Okay, so CSMA CD is always used in, that is the reason the CSMA CD is used in LAN, because in LAN the distance is less, around 10 kilometers. Okay, so now that is why this particular equation denotes that the LAN in LAN CSMA CD is more suitable. Okay, so now now another one, you can also extract out other points like n is directly proportional to 1 over 1 plus L, so it will be directly proportional to L. Okay, so it means that if the length of the packet is higher, the efficiency will also be higher. We already know, so bigger packets, more efficiency. Okay, now if your length of the packet is less, the efficiency is also high. So smaller packets, less efficient. Now okay, so now I'll go with the you have already seen that how can you there will be a collision. So we have seen that there will be some collision. You already know that there is a collision, so from A to B. Okay, so this is the main part here. Okay, so from A to B, when they are transmitting the packet from A and B at the same time, there will be some collision, and the collision signal is then transferred to A. Okay, so now the question here is when to transmit again. Okay, so when to transmit again. Now the main thing that you already know that when A will see the collision signal, it will be transmitting the packet. It means that A knows that my data that I'm sending is collided with another data, so I have to retransmit the data again. Now the main question is when to retransmit again. Okay, so it is the main question. So for this particular question, back off algorithm is there. Okay, so back off algorithm. Okay, so it is very simple. I'll show you by taking a simple example. You will easily understand it. I'll also show you the disadvantage of using the backoff algorithm. Okay, so now actually backoff algorithm only tells you the waiting time. So how much amount of time a station waits before transmitting the packet again. Okay, so suppose I'll taking any example. You can take example another example. I'm taking one example here, that is uh, uh, when this station A and B is transmitting the data. Okay, so suppose both of them are transmitting the data, and at the same time they got here they got a collision. So what will go, the collision signal will send back from both ends. Okay, so now there are two terms you have to know. So that A was sending the first packet. Suppose A was sending the first packet, B was also sending the first packet. Okay, so now N denotes the number of collision number. So here N denotes the collision number a packet is involved. Okay, so collision number for packet 1. Okay, so collision number for packet 1 is now 1. Okay, so because the packet that A has sent towards the network, it is involved in the collision, so it means that this packet 1 is one time involved in the collision. In the similar way, collision number for packet 1 of B is also 1. Okay, so already know. Okay, so now how how you now what is the next step here? The next step here is you assign a random number between A and B. Okay, so now what is the random number? So again, algo says both of them choose a random number between some range. Okay, so here there is some range, you choose a random number. Okay, so now what is this range? Okay, so range is always 0 to 2 raised to power n minus 1 for A, as well as 0 to 2 raised to power n minus 1. Okay, so this n is your collision number, the number of times your packet is involved in a collision. Okay, so that is the collision. Okay, so now because if you find out now the range here, because n is 1 here, it will become 2 raised to power 1 minus 1, so it is 0 to 1, and in the similar way it will also be 0 to 1 for B. Okay, so it means A can choose any number between 0 to 1, and B can choose any number between 0 to 1 here. Okay, so there is no definite, there will be no in between numbers. So it will, the four possibility that can happen is either A can say choose 0, in the same way B can also choose 0, in the similar way choose 0, it can choose 1, it can choose 1, it can choose 0, it can choose 1, it can choose 0. Okay, so suppose what in this particular scenario, what happens if they both choose the same 0, it means for 0 actually means here that they are not waiting for some time, they are directly sending the packet. Okay, so 0 here means no wait. Okay, so again there will be a collision here if they are not waiting, again sending the same again sending the data at the same amount of time, there will be a collision here. Also they will wait for 1 unit time and again send the data at the same time, there will also be a collision. Okay, so both of the time there will be a collision. But here here is saying that A will wait for some time and A will directly send the data, B will wait for some time. Okay, so in this particular case your A won. Okay, so your A transmission is successful. In a similar way here B will not wait, A will wait for 1 unit time. Okay, so in this particular case your B won. Okay, so these are all the possibility that can happen between this 0 and 1. Okay, so again your I can say that if I take this particular scenario, if I take this particular scenario, it means that A's waiting time, A's waiting time is 0 and B's waiting time is 1. Okay, so 0, suppose there is some time slot that is assigned to every stations here. So suppose some time slot is assigned to every station to transmit. So for this time slot such that there is no collision, so it will be again some particular number, so that when A is sending the data, that when A is sending the data, no other no other station is sending this data. So this will be your time slot. Okay, so for this particular time slot, your B will be waiting. Suppose there is some time slot. Okay, so I can refer that 0 time slot here, and here will be 1 time slot. Okay, so whatever is the time slot, it will be directly multiplied. I can say directly that for 1 unit time we will wait, but A will not wait. It will, after the collision, A will directly send the data. Okay, so suppose I am taking the same example, because I want to show the disadvantage of this algorithm. Suppose that in this the probability of collision, if you find out the probability of collision in this case, now what is the probability of collision here? So probability of anything is favorable outcome over total outcome. Okay, so total outcome here is 4, favorable outcome for collision is 2. Okay, so it is 1 by 2, between 50% chances of collision. Probability that your E will won, E will get to transmit the data 1 time out of 4 times, so 25% chances. And for B also it is 1 by 4. Okay, so you're seeing here both the winning probability of A and B is same, but the collision probability is more. Okay, so suppose I'm thinking that this particular time E won. Okay, so provided that A won, now what will happen? So it means that A have successfully transmitted the data. Now this is your second time. Now suppose A won. Okay, so after A won, it means A has successfully transmitted the data. Now what will happen? Again, there will suppose there in the second time there is also a collision. Okay, so when collision occurs, now this is this is the second packet that A is transmitting. Again, this is the first packet that B is transmitting. Okay, so the collision number, I think, what is the number? N here. Sorry. The collision number that this packet is involved in a collision, this second packet is involved in the collision first time. So the collision number for this packet is 1, but the collision number for this packet is 2, because the first packet of B is included in the collision second time. Okay, so it has collided with A before with the first packet. Now it has collided with again A's second packet. Okay, so the collision number that this particular packet, the collision number denotes that a particular packet is involved in a collision. Okay, so this first packet is involved in the collision second time. So that is why I'm writing here 2. Now you see what will happen here: 0 to 2 raised to power n minus 1, 0 to 2 raised to power n minus 1. Okay, so now 0 to 2 raised to power 1 minus 1, it will be 0 to 1, but see here 0 to 2 raised to power 2 minus 1, it will be 0 to 3. Okay, so now if I take the all the possible cases now, if you take all the possible cases here now, you will get all the possible cases. So it will be 0 from A side, B side, it will be 0 1 0 2 0 3. Okay, so sorry, we have four zeros: 0 1 2 3. For 1 it will be 1 1 1 1, 0 1 2 3. So this will all be the possible cases that can happen. So A can wait for 0 amount of time, B can wait for 0 amount of time. In this particular case, your collision will occur. A can wait for 0 amount of time, B can wait for 1 amount of time. It means that A will get to transmit again. Okay, so it means A will transmit the data and B will wait for 1 unit time. In this particular case, A will again send the data, B is waiting for 2 unit time. Again, A has 1 in this case. Again, in this case, A has also 1. Okay, so now in the second one, now A will wait for 1 unit time, B will sending the data. In this particular case, B won. Okay, so because A is waiting for 1 unit time and B is directly sending the data. But see here, there will be a collision here. And now see, A is waiting for 1 unit time and B is waiting for 2 unit time. It means A get to send the data earlier. So it means A won here and again A won here. Okay, so now if you check that probability again here, provided that A has won the first collision, A has won the first collision. So again, the probability I'm counting here is provided conditional probability that A has already won here. Okay, so that is how this probability is. Now if you found the probability of collision, here is collision, here this collision, this collision. So 2 times out of 8 times. Okay, 1 2 3 4 5 6 7 8, total 8 cases, it will be 1 by 4. So now probability that A will get 1, A is 1, 1 2 3 4 5 times. Okay, 5 times out of 8 times. In the similar way, probability that B has won is gone down again, that is 1 by 8 times. Okay, so if you are seeing here, this is around 25%, it is around 62%. Okay, so if you find out, it will be around 62 64%. Okay, it 6 the 48 20. Okay, so 62%, around 62%. And B probability has reduced even further. Okay, so now if I again assume, because the probability of A is higher to win again, if I again assume that if I take it to third case, that third case will be that again A has won. Okay, so second time A has won, now A is transmitting the third packet. Okay, so if I'm still just, it's an assumption that the A has won again, because the probability of winning A is more. Okay, so now if this happens, now what will happen? A here and then B here. So A is transmitting its third packet. Okay, so B is transmitting its first packet. Okay, so when suppose the same collision, if a collision occurs again, now it will again have to choose a random number. Okay, so this packet is involved in the collision first time. So third packet of A is involved in the collision first time, but the first packet of B is involved in the collision third time. Okay, so now see, the here the number will be 0 to 1, but here the number will be 0 to 2 raised to power 3 minus 1. Okay, so it will be 0 to 7, I think. Okay, so now see the probability. If you find out the whole cases from A and B, it will be 0 0 0 0 1 2 3 4 5 6 7. Okay, see 8. Okay, so it will be 0 1 2 3 4 5 6 7. And again if I take the cases for 1, so 1 1 2 3 4 5 6 7 8. So again it will be 0 1 2 3 4 5 6 7. Okay, so now if you find out, it is a collision. Here A is winning, 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 here also A is winning, here also A is winning. Okay, so check here, here B is winning, here collision, here again A is winning, 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 A is winning. Okay, so if you find out the probability of A to be won here, it is 1 2 3 4 5 6 7 8 9 10 11 12 13. 13 out of 16 times A is winning and B is winning only one time out of 16 times, and the collision here is two times out of 16 times. Okay, so this is collision and this is collision. Okay, so if you see here, the back of algorithm has one drawback. The one drawback is if a particular packet has won one time, the next time it will again win the race, will further be increased. Okay, so check here, the in this particular case, if I start from the first case of the backoff algorithm, you will see the probability of winning of A and the probability of winning of B is very similar, that is 1 by 4 1 by 4. Now suppose A has won this particular race, so any one station has to win the race. So suppose A has won this particular race. Now you will see that the probability of winning A, if you're seeing here, the probability of winning A is further increased. Okay. Again, if this particular station won, the probability of this particular station will increase. It is increasing at a very high rate, if you're seeing here. Okay. The first conclusion that you can find out, that if you're using a backoff algorithm, and in a backoff algorithm is one, if one station won, the probability of again winning the collision, what is the transmission, again winning the transmission will further be increased. Okay, another thing you can observe is the probability of collision. With the probability of collision here is 50% in the first one, and if you see, the probability of collision here is only 25%, and the probability of collision here is further reduced. Okay, so it means that the backoff algorithm has some advantage, that it avoids the collision, it is avoiding the collision, but actually uh, the another station actually has a less probability to transmit. Okay, so it has advantage that it definitely decrease the amount of collisions, but again there is a disadvantage of this as well. Okay, so this advantage is called your capture effect. Okay, so what actually is a capture effect here? The capture if if A has won in collision, if I write it, if A has won in first collision, the probability of winning the its winning probability in second one, its winning probability in its winning probability in second collision will get increased. Okay, so that thing is referred to as your capture effect. Okay, so because this particular effect can lead to starvation of B, that B will never get a chance to transmit your packet. Okay, so advantage, it has advantage that the collisions are decreased, the collisions are decreasing exponentially at every turn. If you see that the collisions are decreasing, they are decreasing exponentially. Okay, so it has certain disadvantage, it has a certain advantage also. Okay, so this is again the worst case that I'm taking here, that first time A has won, second time there is a chance of B winning, but I'm taking the worst case because the probability of winning of A is more. So that is why I'm assuming that because the probability of A is winning more, so A will won the second time also. Okay, but if it won the second time, the third time it has a even greater probability. Okay, so that is the only disadvantage of your back of algorithm, that it creates a capture effect. And you are again seeing here that this particular algorithm is applicable only to two stations. Okay, so again this is also one disadvantage, that if you're seeing here, it is only applicable to two stations here that want to transmit. Okay, now there is another access control method that we have to see, that is your token passing. Okay, so just let me open the screen. Okay, So now in this particular token passing here, before going into token passing, you have to understand some terms in this particular thing. That is the time. Okay, so in this particular token passing, the time is also sometimes given in bits, or sometimes the time is given in meters. Okay, so you have, if you want to convert into seconds, there are some terms. Okay, so now what exactly it means that suppose your transmission TP is given to given to you like in what 20 bits. Okay, so if your propagation is given in 20 bits, what you do, you take your TP. So this is the length that is given. So I have to divide it by some bandwidth. Okay, so it is again L by bandwidth. Okay, so in order to find that transmission delay in seconds, you have to divide this particular bit that is given to you by a bandwidth. In the same way, if your propagation delay is given to you like in terms of meters, okay, so 100 meters, 200 meters, it can also be given like this. If it is given to you in terms of meter, it means that they are giving you the time in terms of distance. Okay, so how can you get the time in seconds? So it is TP, you divide this particular distance by velocity, you will get in seconds. Okay, so again the graph for this one is, so again there are many time of conversions that are given here. So if you are given the time in meters, if you are giving the time in meters, if you want to convert this time to seconds, what you do, you divide it by speed or velocity. Okay, so if it's given in meters, you divide it by the speed, or the meter means it is given by the distance, you can divide it by speed or velocity. Okay, so from seconds, if you want to convert it to meters, you can also multiply it by speed, there is no problem in that. Okay, so if it is given in meters, you want to convert it to, if it is given in seconds, you want to convert it in meters. So what you can do, so you can take the time and you can multiply it with velocity. Okay, so seconds into velocity. If you want to convert it into, if your time is given in bits, bit means you are given in the terms of length. So you should divide this particular time by bandwidth to get in seconds. Okay, you already know length by bandwidth is your transmission propagation delay. Okay, so actually it is propagation delay, but it can happen that your time is given is in terms of bits. If they are given in terms of bit, it means they are giving you the length in terms of propagation delay. If you want to get your time in particularly in seconds, you just divide it by bandwidth, whatever is the bandwidth. Okay, so you can take another example. So if I want to say that how many meters, so if I ask you the question, how many meters is 10 bits, 10 bits is how many meters? So if I ask you this question, when you are given the bandwidth as 4 Mbps and velocity is again the speed of light, that will be 2 into 10 raised to power 8 meter per second. Okay, so you know that 10 bits is how many seconds, you have to find out. So 10 bits is actually your uh, 10 bits is how many meters. Okay, so this is in meters. Okay, so again if you go to this example, so your time is given in bits. Now you have to convert this into meters here. Okay, so first you have to convert this into seconds. So how can I convert this bits into seconds? By dividing it by bandwidth. So take 10 bits and divide it by bandwidth. So bandwidth is 10 raised to power Mbps, 10 raised to power M means 6. Okay, 6 bits per second. Okay, so now this is your time, this is your time in seconds now. Okay, so now you are here. Now if you want to convert this into meters, okay, so if you want to convert it into meters, you have to multiply it by a speed. Okay, so what is the velocity here? Velocity will be 2 into 10 raised to power 8 meter per second. Okay, so you can easily find it out. So 10 bits, it is 2 into 10 raised to power 9 over 4 into 10 raised to power 6. Okay, so I think it will be, if cancel it out, it will be 2000 over 4. Okay, so around 500 meters. Okay, so if your transmission delay is given that 10 bits is equivalent to 500 meters. Okay, so keep that in mind, this is that terminology that we will use. Okay, so now Another terminology that we will use is token. Obviously, in token passing you have to know what a token is. Another is your ring latency, another is your cycle time. Okay, so token is very simple, so you can easily read it. So token is if you go to some government organization, if you want to update your Aadhaar card, okay, so you will given you have they will give you a token. So at that particular token will be like 15. Okay, so if your token number is 15, when 15 number is called, you go to the counter and say my token number is 15, please update my Aadhaar card. Okay, the same concept in this one. Okay, so for every station, the first of all the station will be connected in the circular form here. Okay, so now these are different station, four stations that are connected in circular. Now, if any station want to transmit the data, they will have a certain thing called token. Okay. So if the station one has a token, then only it can transmit the data. Okay. So if uh, token out of these four station, only one station will have a token at one time. Okay, so if station 1 has a token, only station 1 can transmit the data. Okay, so if station 2 has a token, only station 2 can transmit the data. Okay, so token is a small message composed of special bit pattern. Actually it is a special bit pattern, like unique pattern, uh, uh, unique pattern thing. Now it represents the permission to send the data packet. A station is allowed to transmit a packet if and only if it possesses a token. Okay, so this is simple. Now another thing is your ring latency. Okay, so ring latency is time taken a bit. Okay, so time taken a bit that you are sending some packet. Time taken a bit, particularly this bit, to take the whole revolution, to take the whole if you the bit started from here and it come back towards this particular thing, this will be your ring latency. Okay, so time taken by a bit to complete one revolution of the ring. Okay, so how much the time will be. Okay, so what exactly the time will be in terms of ring latency. Okay, so again I'll try to just okay, so I'll just try to just calculate the time here. The time here will be, time taken will be from if I just find it out, it will be the, if your bit is from here, so it will go to this station. Absolutely, it will go to this station, and this station will take hold this bit for a certain time, and it will put the bit again onto the link. Again this particular station will be holded for some time, and again it will be released by this station, and from this one, this bit go towards this particular station. This particular station will hold this bit for some time, and it will again release this to the other side. In a similar way, station 4 will also hold this bit for some time, and it will release it. Okay, so first of all the propagation time will be there. So propagation time, to whatever is the propagation time to complete the circle, and another will be the station. The number of stations here are four, so four station will hold the bit for certain time, so I'm calling this as a bit time. Okay, so they are holding this bit, or every station is going to hold bit for at least b time. Okay, so I'm denoting it as a bit time. Okay, so four station here, so I can say to generalize it, that is the total time taken to the propagation time taken for bit to revolve to take the complete revolution, plus but however is the station, so n is the number of station into every station will hold bit for b amount of time, so this is your bit time. Okay, so now it means that your bit time here will be given in bits. Okay, so this TP is in seconds, you already know. This is in bits. Okay, so you have to either convert both of them into seconds, or either convert both of them into bits. Okay, so if you want to convert it, this particular thing, to seconds here, so what you do, actually it is given in bit. It means it is given in length. Okay, so what you do, divide by bandwidth. Okay, so it will be TP plus n by b into bandwidth. So this will be your this is now in seconds, this is now in seconds. Okay, so if you want to convert it into bit. Okay, so if you want to convert it in bit, so you don't do anything for this one. So for this TP, how can you convert this into bit? So actually your TP, so see here, Second, we have to convert it into bits. Okay, so go there. Second, I have to convert it into bits. I have to multiply it by a bandwidth. Okay, so you can say TP into bandwidth. Okay, I think it's plus. Yeah, it's plus. Okay, so either this is also true or this is also true. If I show you the term here, so the ring latency is given by this dy b over plus n by b. Okay, so dy b here is your transmission propagation delay, and n by b is the time taken by every station to hold the bit. Okay, so it will be, I think it is given, yeah, this one. So the ring latency is given in two terms. You have to convert this particular thing into seconds. So for seconds the formula is TP, this one, and for bits the formula is given like this one. Okay, so if I go back there, I have written the same formula here. Okay, so TP into bandwidth plus n by b is in terms of bits. So if you can check it, TP into bandwidth plus n by b. Okay, so TP into bandwidth plus n by b, and in seconds it's TP plus n by b, n multiply b by bandwidth. Okay, so if you check it here again, TP plus n by b over bandwidth is in terms of seconds. Okay, so it depends upon you whatever you want to choose. Okay, so now again the third and the final term is your cycle time or the total time. Okay, so cycle time or the total time. So now the cycle time here will be, it will help in calculation of efficiency, because you know efficiency is useful time over cycle time or your total time. Okay, so time taken by the token to complete one revolution. Now it is not talking about a bit, it is talking about the whole token. Okay, so the time taken by the token to complete one revolution. So suppose that if the token is here, if I have to complete the one revolution uh, again. Okay, so every station, because if the token travel from this to reach here again, that it means every station will get token for at least once. Okay, so if suppose one has got the token and it has released some packet, and after that two will also get the, it can get its turns, and this will hold the token for some amount if it had transmitted. For 3 also it will get some amount of, and so some amount of time for this token, and it will release its own packet, and 4 will also get its, till it reaches the same there. Okay, so now what is cycle time here? Time taken by the token to complete one revolution. I'm talking about the token, not the bit here. Okay, so if you calculate here, the time taken will be, so if you find out what will be the time taken here. So again, the propagation delay of the this particular token for the whole circle will be TP. So another one will be every, now every station will hold this token, because because in the previous one a bit is also holded for some amount of time. So every station will hold this token. So this particular time will be referred to as token holding time. Okay, so every station will hold this token for some amount of time. Okay, so that will be your total time or your cycle time. Okay, okay, so if you find out the cycle time is again n into THT. Okay, so THT is your token holding time. Okay, so now again I'll complete this particular topic in the next one. Okay, so if you have any doubt, ask me, or you can move on to the next one.